Hi, I'm Stephens-Davidowitz, and I'm going to be giving a talk about the FM index. So the FM index is this nice data structure that allows you to search on a string while it's still compressed. So this is nice for very, very large strings, and I'll explain more about that in a second. So the FM index was invented by Ferragina and Manzini in 2000. However, it was not named after them. It was named the full text index in minute space. So this is a classic strategy when you don't want to name something after yourself. You name it after something else and make it sound like it was named after yourself because it's considered kind of obnoxious to name something after yourself. So anyway, uh, first a quick disclaimer. This is going to present some original work. If you look up the FM index, you'll see some stuff that's slightly different. This is all based on ideas that are thoroughly researched and from other papers, but for the interest of presenting things cleanly, I'm going to present my sort of own algorithm. It's going to be slightly different than the one that you normally see, and I won't follow all the conventions that everyone else will follow. So if you do further research on this, you'll see that things are a little different, but hopefully it'll be clear what I did. So anyway, let's go on. So why do we care? First of all, DNA is a very, very large string. So here's an example. This is the beginning of human reference genome. I'm not sure what version. Maybe it doesn't matter. And this goes on for 3 billion base pairs. So anytime you see the word billion, you know that you're dealing with stuff that you probably shouldn't be dealing with. So this is very scary, and it's difficult to work with. So let's think about what one would want to do with a very long string. There are two incredibly basic things that you might want to do. First of all, you might want to store it. A very long string is useless to you if you can't hold it in your memory. And since this string is so incredibly long, we don't want to store it in like a 3 GB file. It would be nice if we could compress it down in some way. In addition, you might want to look for stuff in it. I might want to look for a particular gene, or I might want, if I'm doing alignment, then I might want to find where one string aligns to this very long string. In order to do that, I need to do a search in the string. So we're going to talk about how to do that. So first of all, let's talk about string compression. So again, we have this very, very long string. Here's, again, the beginning of the human reference genome. But you can see it's remarkably redundant. If I were to describe this string to you in words, I would say, well, you got these 6 base pairs, T, A, A, C, 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 and then they repeat for a bunch of times, and you've got to count the times, and then towards the end, they change a little bit. It doesn't, I don't have to say all of the base pairs to communicate this to you. So we can think about how to try to store a string without having to write down all the base pairs, because it's clear that you don't need to. So a really, really natural idea is what's called run length encoding. So here, if I have 8 C's in a row, I write C followed by 1000, and the reason for that, 1000 is 8 in binary, so instead of actually writing out all the C's, I just say, hey, look, there are 8 C's here, and that's a very natural way to do it. And this has one really, really nice property, which is if we have this really long stretch of C's, like say n C's, then we compress down to about log n C's, which is much, much smaller for very large numbers. So that's very, very good, and that suggests that we should try to make run length encoding work. So let's just try it. Let's apply run length encoding to this string, and you can see it doesn't go well. Indeed, the string gets larger, which is bad. But then we can notice something. Note that C was encoded with a C followed by a 1 and then 3 zeros. And if you look at every base pair in this string, so every character except for the 1s and 0s, it's always followed by a 1. And that's kind of natural. Every binary number starts with a 1. So we can just assume the 1. We don't have to write it. So we can just remove that 1. So instead of C100, now we have just C000. And if we apply that to our string, then indeed our string does get shorter. In fact, it gets shorter. It's about 83% of the size of the original. But that's slightly false, because in order to do this, I increase the alphabet size. So if I were trying to compress this string as well as possible, there are only 4 base pairs that occur in the human genome, so I can encode 4 base pairs in 2 bits, but the second I add another character, I have to go up to 3 bits. So that increases me by 50%, And then I have 124% compression, which is not compression, that is expansion, which is not good. Now, of course, depending on your implementation, this increasing the alphabet size might not matter, but it's something to keep in mind. So this didn't work very well, but because run length encoding had this really nice property that it takes a string of length n and could potentially compress it down to a string of length log n, which in some sense is optimal, we want to make this work. So let's look at our string again and see if we can play some tricks with it to make this work. So one thing to notice about this string, look at every place where there is the base pair t. Note that every time there is the base pair t, it is preceded by a character c. So the only character that can precede a t is a c. So this suggests that we might partition the string into subsequences by the next character. So, for example, we can list out all the characters in our string that come before an a. Here they are. It turns out, if we go back to our original string, you can see that the only characters that come before an a towards the beginning of the string are a's and t's, right? So this string begins with a's and t's, and towards the end it gets a bit, it has a few c's thrown in there. Here are all the characters that come before a c, and here are all the characters that come before a t, and this was sort of our purpose. You can see that now we've successfully gotten a very, very long run of c's. So that's wonderful because that's what run length encoding knows how to deal with. However, why stop there? Why not partition the string into subsequences based on the two next characters? So here we have all the strings, all the characters that are followed by an A and then another A, all the characters that are followed by an A and then a C and then a C, etc. And you can see that there's tons of redundancy here. So this is wonderful. Let's apply run length encoding. So that's great. We shrunk everything down a ton. But this leads to a natural question. How are we going to actually represent this in memory? So one way to do it would be to write down the suffix AA, and then after the suffix have some kind of separator character, and then write down the characters that come after it. And then same thing for AC, same thing for CC, etc. But I'm going to do a slightly different way, which will be more evocative for what I'm going to do later. So what I'm going to do is start the character structure, start the data structure with a list of characters. So the only characters that appear here are ACT. Then I'm going to sort all the suffixes alphabetically, and I'm going to include here suffixes that aren't there. So you'll see now the suffix AT is here, and the suffix TC are there, and they're just followed by the empty string because they don't come up. And then I'm just going to sort of collapse everything down and write the strings out in order. So now I have my list of characters, followed by a separator character, followed by the characters that come before the first alphabetical suffix, and then the characters followed by the second alphabetical suffix come after a colon, and where I have where a suffix, doesn't get used, I have a double colon, so two separator characters. So in this way, I don't actually have to write down the specific suffixes, which is nice. Depending on the specific parameters of the string, this could save me or lose me, but this idea is going to be helpful for us later. And it turns out after we imply this, we get 57% compression. If we consider the alphabet size increase, it's only 86% compression. That's still not great considering how incredibly redundant this string is. So of course we could go on. We could partition the string into subsequences by the next 3 characters. I'm not going to bore you by actually doing this, but I did do it, and here's the result. You get slightly better compression, but still not great. And you can think that, in general, it's not really clear how much to look back. And indeed, sometimes looking back might hurt you. If you recall, for T's, it turned out that we only needed one look-back character for T. So every time that I saw a T, the character before it was always a C, regardless of what else happened there, regardless of whether it was TA or TC or whatever. So as a result of that, if I consider longer suffixes that start with T, I won't gain anything, and I do lose things because I have to consider more suffixes. So this leads to a natural question: can we generalize this in some way, or do we have to just keep kind of coming up with a look-back number? And the answer is, of course, that we can generalize this, otherwise I wouldn't be giving this talk. And the guys who first did it were Burroughs and Wheeler, and they did it in 1994. I think, actually, Wheeler did it in 86, but didn't bother to publish it until 94 with Burroughs. I could have many of those facts wrong. So let's look at a slightly shorter string so we can look at this. So the string we're going to be looking at is talk, 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 which I believe is thank you 3 times in Icelandic, spelled wrong. And I've thrown a $sign at the end of the string. So this is just a standard convention. You can think of it every time we have a string in memory, or almost every time you have a string in memory, it's going to, at the very end, have some sort of end of file character, or end of string character. But also, this $sign is going to make our life easier later. So instead of listing all suffixes of a specific length, let's list all suffixes that appear in this string. So the suffix $sign appears in the string. In particular, the last C in the string has the suffix $sign. The suffix C $sign appears in the string. In particular, the second to last C has the suffix C $sign. Then there's also the suffix CC $sign, etc. So we essentially just are going to write out the string backwards. I can't fit them all, but that'll suffice for our purposes. And then what I'm going to do is I'm going to write the character. Oh, sorry. And then I'm going to sort these suffixes alphabetically. Similarly to how we did before, now we have variable length suffixes, and we have a lot of them, but it's the same idea. We want to sort them alphabetically so that in the hope that we won't have to write out all these suffixes. Now I'm just going to write the character that precedes each suffix. So here now there's a unique character for each suffix because each suffix is unique. So you can stop and check that I've done what I've claimed I've done. And now you can notice that this data structure has some nice features. For example, suppose I want to find all the strings that precede the characters AA. Well, here they are. They're all the things that come before these suffixes right here, so there are these 3 T's on the left. So that suggests that this data structure might have some nice properties, and we might want to consider it further. The big question with this data structure is, suppose I only give you this string right here, this string that's now represented vertically, so CTTT, etc. Can I find the whole string just from this? And you might think the answer is obviously no. In fact, the answer is yes, which is good, because otherwise I wouldn't be giving this talk again. The other thing to notice about this string is that it's highly redundant. Why is it highly redundant? Well, it's highly redundant because the string has structure. So, for example, the fact that T always precedes an AA here is the reason that we have 3 T's in a row. Similarly, after those 3 T's, the fact that AAA always precedes AC here is the reason that we have 3 A's in a row, etc. So, a string with a lot of structure will produce a very redundant string here. So this string we call the Burrows-Wheeler transform, and the Burrows-Wheeler transform in general takes some structure and leads to redundancy. So that's very nice. Or when I say redundancy, I suppose I mean repetition. So let's play with this data structure some more. One way that one can imagine inverting this operation, so going from this string on the left here to the original string at the top, would be to be able to find, given any character, what character precedes it in the original string. Given any character on the string on the left, find the character that precedes it in the string above. So let's look at this character C, and let's try to find the character that precedes it in the string above. So how do we do that? Well, if we want to find the character in the permuted string that corresponds to the character that comes before this C in the original string, that's equivalent to finding the character that comes before the suffix that starts with this C, right? So we have the suffixes sorted alphabetically, so we should know where that happens. In particular, there are 7 characters that come alphabetically before C in the permuted string. We can count these in the permuted string. I'm representing them here on the suffixes because it's easier to see them. So the 7 characters are 6 A's and $1. And by looking at the permuted string, we can see that this is the second C in the permuted string, so it must be the second, it must start the second suffix. Here are a prefix, that's a mistake, whatever. So this C must start the second suffix that starts with a C. So, based on that, we know that we're looking for the 9th character, because the first 7 characters will be characters that that come before a $sign or an A, The 8th character will be a character that comes before the first C alphabetically, which we are not, and the 9th character will be the character that comes after the second C alphabetically, which is RC. So now we found the character that comes before it, and if we do this starting from the $sign, we can backwards build the entire string. You'll notice that everything's sort of backwards. This is a convention. People prefer suffixes instead of prefixes for whatever reason, and it's what we're stuck with. So now let's look at this string horizontally instead of vertically. Here's the full Burrows-Wheeler string. You can see that it's highly redundant. In particular, it ends with 6 C's, and you can imagine that if I made this a longer series of repeated strings, this string would become even more redundant, which is wonderful. And let's make a little more formal what we just did before. So let's define count x to be the number of characters alphabetically smaller than the character x in the string. So here we have the counts of the various characters. So count $sign is 0 because no characters come before $sign alphabetically. Count A is 1 because only $sign does. Count C is 7 as we saw before because there are 6 A's and 1 $sign. Count T is 16 because there are 9 more C's to add to that. And count G is 19, which is the total number of characters in the string since there are no G's. And now we're going to find rank of xi to be the number of the number of occurrences of x in the first I characters of the transformed string. So, for example, the rank of A of 5 is 1 because the A in the 5th position of the Burrows-Wheeler transform is the first A in the Burrows-Wheeler transform. The rank of T in the 4th position is 3 because that's the 3rd T that appears in the Burrows-Wheeler transform. Now, using those, we're going to define a new operation, which is traditionally called LF, for last first. I don't think that the name is particularly illuminating, but this is the function that we apply repeatedly. So the LF of a given index I is the count of x, where x is the character in the ith position of the transformed string, plus the rank of x at I. So let's do an example. Let's do last first of 5. So first we find the 5th character. That's this A here. Then we know that the last first of 5 is the count of A plus the rank A at 5. So the count of A is the number of characters that precede A alphabetically in the entire string. There's one of those, $sign, and the rank of A at 5 is the number of A's up to the index 5. So there's only one A up to the index 5. This is the first A. So our answer is 1 plus 1, which equals 2. And this means that the character corresponding to the character that precedes this A in the Burrows-Wheeler string is T. This T in the 2nd position here. So LF tells us the index of the character that comes before us. So this is wonderful. Now, how can we use this for compression? Let's look at our longer string again, and here I've added a $sign, as our convention dictates. Let's apply the Burrows-Wheeler transform. We get this crazy string here. You can see it's incredibly redundant. And then let's apply run length encoding, and you see it gets much, much shorter. Sorry for switching fonts there. That was because midway through the first time I gave this talk, we had a bet about whether or not my string lengths were correct. So I changed to a fixed width font. Anyway, you can see that this gets much, much shorter, and that's wonderful. Indeed, we get 23% compression, or 34% after increasing alphabet size, so that's quite impressive. Much, much better than we did before. But if our string is extremely long, this string is not quite extremely long, but one can imagine, 3 billion base pair strings, so maybe even the compressed string could be very long. Computing LF the original way that we did might be a little slow. In particular, in order to compute LF in general, we'd have to look through the entire string the way I originally showed it. So let's see if we can do it a better way. Now let's recall how we compute LF. LF is given by count plus rank, where count is the number of characters that are alphabetically smaller than x, and rank is the number of occurrences of x in the first I characters. So first of all, there are only a few characters to store, So we can just store, I'm sorry, so let's say we want to find LF of this specific C, I should have said. So there are only a few counts that are possible, just one for each character. So we can just store these beforehand. So here I have the count of $, the count of A, the count of C, the count of G, the count of T, and it's traditional to end the count array with the count of the total number of characters, which is 222 here. So count is easy. We can handle count very, very simply. How do we handle rank? Well, we handle rank by just sort of shoving into our string at various points some counters that are more specific. So each of these counters, so the first counter here is present at the position where there have so far been 2 A's, 3 C's, and 6 T's. Right? So now if we want to compute LF of this specific C, what do we do? Oh, excuse me, and we separate these by constant distance. So if we want to compute LF of this C, what do? First, we walk back from this C until we see another C or a counter. So here we found another C, so we remember that we saw it. And then we find this counter, and we see that, I'm saying C a lot, we see that we've seen 15 C's. That this counter has 15 C's and that we saw 1 C, so our total number of C's must be 16. So this must be, so our rank must be 16 here. Then we look up the count of C, which here is 77, and then we simply add them together, and we find the 93rd character, and it turns out that the 93rd character is the character that precedes this C. So that's wonderful. So if you think about it, this operation ran in constant time. I had to walk back at most a constant distance, and then I had to look up from a constant lookup table. However, that's not quite true. I've sort of lied to you. It actually takes log n time. And the reason that takes log n time is because just to write out the index of a character in this string can take log n time, right? So it takes log n characters to write a number that's n long, a number of size n, but luckily, even in the human genome, log n is less than 32. It's close, but it's less than 32, and in general, we're working on 32 or 64-bit machines, so we typically think of writing out strings up to length 32 as taking constant time, because in practice they do. However, if you're making some really crazy optimizations and trying to use individual bits as opposed to words in a machine, this might actually matter to you. So it's an important thing to keep in mind. So let's talk about some basic optimizations. If you're not concerned about the details, feel free to skip ahead. So first of all, we don't need to encode in the way that I did before, where you write out all the suffixes and sort them. Indeed, you can encode efficiently. I'm not going to bother to go through the algorithm, but the short answer is that you use a fast suffix array or suffix tree algorithm. And there's tons and tons of literature on this topic, so simply Google it. Another thing to do is to use move to front encoding before run length encoding. So move to front encoding is when, instead of writing down a specific character, you simply write down the number of unique characters that have occurred since the last character. It turns out, since DNA is highly redundant, this will end up with fairly low numbers in general, and writing fairly low numbers will be nice. More importantly, after the run length encoding, you should apply a Huffman code. This will save you a lot. In particular, Huffman code is prefix free, so we can have varied length strings, and we don't need separators. That saves you a lot. In addition, you can worry about optimizing spacing between the counters. Logarithmic space is actually probably better than the constant space that I suggested. And on top of all that, there are tons and tons of little things that you can do. But it's worth noting that the algorithm that I just described to you is essentially bzip2, so it's basically the best way that we know how to compress a string, and it's really, really simple. So we've compressed a string, we've invented bzip, that's great. Now we have a new goal. Our goal is to search efficiently. So let's look at how people normally do this. Let's go back to our string talk, 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 and let's just do something very similar to our Burrows-Wheeler transform from before. Let's write out all the suffixes in talk, talk, talk in alphabetical order, and then let's simply write the index of the place where they started. So for example, the first suffix here is $. the dollar sign appears in the 19th position of this string, so I write 19. The next suffix is AACCC dollar sign, and that occurs 5 characters before, so I write the number 14. Now, how do I use this suffix array to search? Well, it's fairly easy. Suppose I want to find all occurrences of the string AC. Well, the obnoxious answer is, well, here they are, right? And why do I know that they're here? Well, because all occurrences of character AC must start a suffix that starts with the characters AC. So let's turn this into an algorithm. It's really not hard. First, we're going to start in the middle of the suffix array. I'm essentially just going to describe binary search here. So we see in the middle of the suffix array, we have the number 16. So we look up the 16th character. And then we simply compare that character to our search string to see if we're too high or too low. So here C comes before the suffix, comes after the suffix AC. So we're too high. So we want to recurse on the beginning half of the array. And obviously, if we keep doing that, we'll be able to find the index before the start of this list of ACs and the index after the start of this list of ACs. So we'll get all occurrences of the string AC. So that's wonderful. But this looks a lot like BWT. So maybe we can just use the BWT transform to do this. Sorry, the BW transform to do this. So let's go back to our BW transform. And let's see if we can do something similar. Let's find all base pairs that come before an A. So this isn't quite as good as finding all occurrences of A, but it's kind of the same thing, right? So here's what I'm going to do. First, I'm going to find the first and last A's in the Burrows-Wheeler transform. Here they are. And let's think about what these A's are. Well, the first one is the A's whose suffix is lowest alphabetically. You can check that visually, and you can think that that actually does make sense. The last one is the A whose suffix is highest alphabetically. Right, so if I apply LF to both of these values, what do I get? Well, I get the character that comes before the suffix starting with A that is lowest alphabetically, and the character that comes before the suffix starting with A that comes last alphabetically. And if you think about it, the interval between them is going to show all the characters that come before an A. So that's wonderful. And this is very, very similar to searching. And indeed, we can do this again. So suppose I want to instead find all base pairs that come before 2 A's. Well, I can stick in this interval that I already have and note that, and just again, look for the first A and the last A, apply LF, and now I found all the characters that come before the string AA. So with this, I can, in general, find all the characters that come before any given string. And I can find their indices in the Burrows-Wheeler transform. And one of the things that that gives me, which is kind of nice, is it tells me how many there are. So if I know that the indices span 3 characters, then there are 3 instances of the given string. If I know that the indices span no characters, for example, the last index is less than the first index or something crazy like that, then I know that that string is not present at all. So that's a nice thing to be able to do, but it's not perfect. But this is really nice, so let's see if we can do it more efficiently. Because keep in mind, the first thing that I had to do was I had to find the first and last A's in the string, and more generally, I have to find the first and last A's in the string that come between 2 indices, right? So when I was back here, I had to find the first and last A's that came in this interval. So let's see if we can do this quickly. I'm only going to worry about finding the last A before a given index. Equivalently, I can find the first A after a given index. You just flip things around. So remember, so it turns out that actually doing this is very hard, but I didn't actually need to use the last A before the red line. I just needed to apply LF to it. So I needed to find the character that came before it. Maybe I can just jump ahead and just quickly find the character that came before the last A before the red line. Turns out that's possible. So remember that we have some additional data. We have these counts here, and we have these little counters spread throughout the string. Here I've only written one of the counters because it's the only one we'll need. In general, there will be many. So let's see how we can do this. Well, first we're going to get the rank of A at this given spot by just walking back to the previous counter. So we walk back and we see that the counter says 3A. So that tells us that the A that comes before this line must be the third A in the Burrows-Wheeler transform. So now we're looking for the third A. Then what we do is we get the count for A. So here the count for A is 1. Sorry that everything's bouncing around. I modified this PowerPoint, or Keynote rather, very, very quickly before doing this to apply some of the suggestions that the people I gave the original talk to was, and obviously I did not do a very good job, but whatever, we'll power through, right? So here we see that the count of the A is 1, because there's $1 that precedes it. So let's think about what that means. Well, that means that there must be the first character in the Burrows-Wheeler string is something that doesn't come before an A, and now we know that the second character is something that does come before an A, and then we just want the third A. Well, we want the character that comes before the third A, so that's going to be the character that comes that's going to be the fourth character, right? So we want the third character after the first one, that's the fourth character. Sorry that everything jumped around so much. Anyway, so we find the character that comes before the third A, it's this T, everything's wonderful, and we're able to do that very efficiently, indeed in constant time. So let's formalize this algorithm. How do we quickly find the character preceding the last X before index I? First, we walk back from I until we see either an X or a counter. Note that if we saw an X, we're done, right? Otherwise, we look up X in the counter and get the rank of X. Then finally, the correct index will just be the count of X plus the rank of X at I. All these steps take constant time, you might notice. Well, actually logarithmic time, but depending on our implementation, we might not care. So that's wonderful, but the holy grail would be to be able to do this on a compressed string. So here's our compressed string again. Let's see if we can do it. So you'll notice that there was sort of an implicit thing that we had to do in the previous algorithm that I didn't even bother to mention, which is to find position I. Now, if we just have some uncompressed string, that's really easy, right? But if I have some compressed string, it's not really obvious where position I is anymore. Because the string has been compressed, so position I could now correspond to a much, much earlier position, and in general, we don't necessarily know how much the string got compressed before it, so we don't know where it went. So how do we handle this? We simply use pointers. So we're simply going to change these counter arrows to now be pointers. I'm representing this by red. So now, just spaced at constant intervals through the compressed string, we have some pointers, and then we simply pick our pointer, pick the first pointer the last pointer that comes before I, and then we just walk up until we actually get to the character I. Now remember that our second step in the previous algorithm was to walk back from I to get the rank of X at I, or to find the first instance of X, but we can actually do this in the first step, right? So we're starting out where that counter is, where we can get the rank, so we can look up the rank. Then we can walk forward to I, and as we're walking forward to I, we can look for an X. And if we see an X, then the last X we see is the one we wanted. And finally, we simply return the count of X plus rank of X at I if no X was found. So that's really easy. And by doing this recursively, we can find all characters preceding any pattern P, and this runs in effectively constant time, or really order of the length of P, but in general, we think of the length of P as being quite small. You know, for biological applications, it's often like 10 or 12 or so. So here are a bunch of details that I'm just going to go through quickly. First of all, you have to worry about how to work in the middle of a binary string. Indeed, this causes problems. So in general, like, you know, you can imagine one of your pointers or one of your counters landing in the middle of some long binary string. And you can also worry about when you might want to locally decompress. So in other words, when you're walking up from this pointer, do you want to actually expand out the binary representation, or do you want to leave it compressed? You often don't want to decompress, but dealing with that is hard. It turns out that dealing with both these things adds a little bit of overhead. You can also think about what the optimal gap is between pointers. Again, I believe it's logarithmic. But it actually turns out that the best thing to do is to have two sets of pointers, so sort of two different groups of buckets, one that are spaced out fairly close together, like log n, and one that's spaced out much farther apart, like log squared n. But in some sense, you can prove that this is sort of optimal compression. Indeed, I'm just sort of going to write this. So here, hk of t is the kth order entropy. And if you don't know what that means, simply ignore it. But if you do know what that means, be impressed. But this isn't search. This is finding characters that come before a pattern. What do we need to do to make it into search? Recall that we were able to do this, and that's really, really close to search. But what are we missing? So we know all the characters that come before the string AA. In order to find all the instances of the string AA in the original string, in particular find their locations in the original string, what we need to be able to do is, given the index of something in the Burrows-Wheeler string, so in other words, given the index of these three t's, find their indices in the original string. So that's what we want to be able to do, find index of a character in the original string from its index in the Burrows-Wheeler transform. So here's the solution. Instead of looking at talk, we're going to look at talkum. So here, m is a special character that we will add. We will evenly space it in the string. So here I've evenly spaced it in a convenient location. The fact that I put it in a convenient location isn't relevant. In general, you sort of put it, roughly every log n spots or whatever. And then we're going to apply the Burrows-Wheeler transform with this special character m in there. It doesn't matter how you represent it alphabetically. I believe here I've treated it as though it came last alphabetically. And then there's one special thing that you're going to do. You're going to tag each of these m's with its location in the original string. So if they're spaced evenly, you can really just tag them with their rank. Here, to make things simpler, I tag them with their actual location. So now, if we want to find the position of this character A in the original string, well, we apply our favorite function, lf. We find the character that comes before it. Turns out it's this t. Then we apply our favorite function, lf, again to find the character that comes before it. Turns out this m. So we know that this m is in the 14th position. We know we've applied lf twice. So we know that that original A must have been in the 16th position. And now we're able to, in constant time, or really in logarithmic time, find the position of any character in the original string given its position in the Burrows-Wheeler string. There's a little bit of an optimization. You can really just tag evenly spaced characters in the original string with an index. So for example, you might write some special characters around a character together with a number to represent that it is that character. And then when you apply the Burrows-Wheeler transform, you simply treat this sort of special crazy A16 in brackets as just an A, as just one chunk that is alphabetically an A. And if you do that, then you'll be set. So let's go through our full compression algorithm with all its functionality now. It's quite simple. First, we add the m's and the $, and we store the location of the m's. Then we apply the Burrows-Wheeler transform. Then we place all our pointers and counters. Then we compute the count array. Then we apply move to front encoding, which again I didn't go through, but it is one step and it's quite easy. Then we apply run length encoding, and then last we apply the Huffman code, which again I didn't go through, but is one step and is quite easy. And it turns out that steps 3 through 6 can be done concurrently. That should be fairly straightforward if you know what move to front is. And there are tons of optimizations here, and in practice, this compression can actually be done very, very quickly. And then we have full functionality. We can search on this string. It's optimally compressed, and searches can be done very quickly. So let's see the final run times after all the subtleties are considered. In order to compress, we only need linear time. In order to decompress, we only need linear time, so that's the best one can hope for. To count the instances of a pattern P, we only need order length P time, which is again the best you can hope for. If we want to search for P, we need a little bit worse. We need order length P plus log n, but that's still not so bad. Again, log n for the human genome was like 30, not a big deal. Actually, we can do a little bit better than that. We can do log n to the epsilon for any epsilon. And this is a space-time trade-off, so if we want a better epsilon, we'll have to store more space. In practice, I think people choose fairly low epsilons, and the space isn't too bad, so that's great. And I've kind of lied to you. Both these counting and searching runtimes ignore the log n factors from writing addresses because in practice they really don't matter, although for theoreticians these are obviously quite important. So that's all I had to say. I hope you enjoyed this, and thanks so much for watching, listening.